Good morning, everyone. Uh, how are we doing this morning? Okay. So, as it says, building resilient systems. Uh, the good thing about this presentation is that I don't need to explain much about resilience because I believe everyone seated here is resilient by nature because you are a Nigerian. I'm sure some of you had to transport yourself here. The amount or your transport fare that you had to pay last month or the last day first when you were here. Let's use last day first. For those that were here last day first and those that are here today, I'm sure they can tell the difference between the transport fare that was used to come here last year compared to what it is this year. But that didn't stop you, did it? So by nature, that means you're resilient. The agenda of the discussion is to do an introduction of what a resilient system is, design principles around resilient systems, operational flexibility, and then the resilient culture and continuous improvement around being resilient, right? So, a system is resilient if it can adjust its functioning period to, during, or following events. Events can be changes, disturbances, opportunities, and thereby sustain required operations under both expected and unexpected conditions. Essentially, what Mr. Eric is trying to tell us here is that if you build a system and the system is able to perform whether or not you had plans for fuel increase going up or fuel increase going down, or there's 1 million people attending GDG, or it's just one person attending GDG, it's all the same to the system. It will take it. Now, before I go forward, just to feel a little bit of the pulse of the room, right? By show of hand, can you show if you are within the product industry or if you are within the product profession, product design, product marketing, product development, product management? Show of hand? Not much in the room, okay. If you're a software engineer, I know these days there's a lot of distinction when it comes to software engineering. Data scientists will tell you they are not software engineers. Machine learning guys will tell you they are not software engineers. To me, I see us doing almost all the same thing. So if you're within the software engineering or development line of work, profession, can I see you raise your hand up? Interesting. All right. Thank you. If you are a QA, you are an engineer, you are maybe like a pen tester, because again, there's always that struggle between QAs, pen testers, and whatnot. Can you show your hands? Wow. We need more QAs in the room. Okay, all right, thank you. Thank you so much. The reason why I'm filling everyone's purse is because I wanted to understand the room and know those I'm speaking to. So at least when I'm speaking, the direction of my conversation would be a lot more sensible to everyone, whether you're a software engineer, QA, whoever you are, however you are, and whatever you do. If you had noticed the first slide, it's majorly resilient systems that are flexible and adaptable that I'm talking about. So when it comes to resilience, there are a number of things that happens, right? The first one, let's say 4 things. The first one is for you to be able to anticipate, for you to be able to monitor, for you to be able to respond. I'm forgetting the 4th one right now, but there are about 4 things that you need to do if you want your system to be really, really resilient. So within the flow of resilience, right, it is important that your system has flexibility and adaptability, right? So essentially, what does that mean? What does that mean to a product design person? What does that mean to a software engineer? I know when you look at the screen, it says hello world, yeah, but we all, whether it's a product, whether it's a software, products are digital, softwares are digital products these days, isn't it? So whether you are within the product team or as a software engineer, it's the same thing. It's still hello world, right? Because the first introduction of your product as a product person is your hello world. Meanwhile, for a software engineer, the ability for me to be able to at least maybe see my login page as a software engineer, probably I would take that as my hello world. So what is the importance of that when you're designing your system from hello world up to the point where it gets to, say, 1 million users, 2,000 users, again, end users, it does not really matter, right? What matters is that your system is flexible and it can adapt to any situation. The difference is this, right? The difference is in you knowing the non-functional requirements of what you are doing. What do I mean by that? As a product designer, let's take for instance, you are developing a software for logistics or for a logistics company, right? I believe your first hello world is probably the ability for a customer to be able to book a ride or order an item and then it being delivered. That's your first hello world when you look at it from the product point of view. How flexible is your system such that, and the funny thing about this conversation is this: we get excited about the hello world. Most of the time, we lose sight of where we are going and then get overexcited about that first win. And believe me, I like small wins as well, but I believe what happens is most of us get lost in that moment and stay within that moment. So, what resiliency does for you is that while you are celebrating your small moments, you are also recognizing the big moments, knowing that there's a possibility that this thing grows, and there's a possibility that your system is able to handle that growth, right? So how do you then design your software, design your product such that it can handle the lowest request up to the maximum request? That is what resilience is about. And that's what we are talking about when we talk about flexibility and adaptability within a resiliency, a resilient system. So your system needs to be able to evolve. Your system needs to be able to adapt. Your system cannot be static. You can't have a static system and call it, or say you have a resilient system. So, again, I hope this is visible enough. This is me giving context to resilient system and using the hello world as an example of that. So if you look at the screen, to your left, I needed to confirm that. To your left is a simple hello world code, right? And to the right is, a more sophisticated hello world code that has resilience embedded into it. I would explain. So the first one just prints out hello world. Simple. No, it's not thinking about anything. It's not bothered about how many people visit it. It's not bothered about how many people wants to print out that hello world. So what it means is that for the first one, if 1 million people visit that hello world and the system which it is operating on does not have the capacity, it means that people will not be able to see that hello world, right? That's what it means for the first line of code. But for the second one, you can see it's not just looking at printing out the hello world, but actually is looking at the input. It's looking at detecting the device. What kind of device are you using, to even interact with what you want to see? And then at the last part is then going into a greeting service to sort of configure and create out an hello world screen for you to see. So the difference between being static and being resilient is what I'm trying to show here. We can actually make this even much more complex if we want to. Not complex, my apologies. I mean more resilient if we want to, right? But to give you an idea of how resiliency can come into what we do on a day-to-day basis, I just wanted to show this context. So, design principles. Again, there are a lot of arguments here. I had to argue with myself while I was doing this presentation. So, but I've decided that I'll put the argument out there, and then it can form part of further conversations that would happen later on when you guys break into the smaller rooms, and then when you meet for your networking to have a conversation. So for design principles, for me, the rule of thumb is keep it simple, right? If you keep it simple, from your simplicity, it can lead to complex, right? Essentially, what I'm trying to say for the design principles is, and this is speaking to software applications or software systems and nothing about product or quality assurance, right? If you keep your applications simple, and it does not matter what technology or what architecture you decide to use, whether it's microservices, whether it's monoliths, or whether it's service-oriented architecture, it wouldn't matter at that point because you've made it really, really simple. And there's a story about the car you are seeing there. I'm sure most of you recognize the car. How many of you recognize the car in the slide? How many of us? Show you over. Okay. I'll tell you about the car. It's to further explain why design principles are important. So modularity. Design systems with modular components that can be easily updated or replaced without affecting the entire system. So I believe this can go across board, whether you are in software or product. Ensure that your design are small, brick by brick, just like a Lego system or just like a Lego brick. If you build them brick by brick and then you bring them together, it makes it easier. It makes it a lot more simple for even people you're working with to understand it. And then the last one is event-driven architecture. So I know this is an architecture as well, but I believe it's quite important to call it out specifically. So it's to create an event-driven system where something happens, and if an event happens, it drives another action by maybe another part or a module within your ecosystem. Let me put it that way. So implement event-driven patterns where components react to events and only interact as needed, making it easier and to add new features or handle spikes in demand. So let me talk a bit about the car. So that's a Bugatti Chiron, if I'm pronouncing it correctly. So that's like a life mode of that car, right? And it's actually built with Lego components, like your normal Lego components. So you can imagine the number of hours it took, the work that was put in for that to be done. Now, let me give you an example. Say, wonderful example. Say you were given this car and then you are driving it on a Lagos road. We all know how Lagos drivers are, whether it's downfall, whether it's keke, whichever one. Choose one. Choose whatever flavor that works for you. And while you are driving on a Lagos road, one of them hits you. Right? What do you think happens to this car? What do you guys think would happen to this car? Do you think it would shatter altogether, or it's going to be a case of, some part of it gets damaged and then it's repairable? What do you guys think would happen? What's going to happen is that whatever part that was involved in the accident would get damaged. But the good thing about it is this: it's going to get easily replaceable. Just go find the Lego parts or the spare Lego parts and then put it. Also, what it means is that you are still able to drive the car. Let me give a really, really typical example. Say the driver's door was damaged, right, in that accident. What happens is that whoever owns the car just takes off the whole of that driver's door, puts it in his boot, or put it over or inside the car, wherever he wants to put it, and then drives off. And when he gets home, he's going to. So imagine a system like that. That's essentially the picture we're trying to paint here. Imagine you designing a system of this nature, where any part of your system is replaceable, is upgradable, is easy to work with, and it makes the whole system resilient. Because what happens is, let me ask a very simple question. The software engineers here, if your application's database is dropped, what happens to any of your applications? For those of us that have built applications in recent times, what happens? And please be sincere. Don't come and tell me here that it will still work. We all know we will see the, what's that page called? The .NET environment calls it one specific name. It shows you one red screen like this, and it's as if the whole world has gone down. For some other languages and frameworks, it's more, maybe a little bit more palatable. It can be a little bit more palatable. Essentially, what I'm trying to say here is, imagine an application of yours where if the database is dropped, even if, and that's the worst that can happen to any application, even if the database is dropped, right, is still interactable, meaning whoever is using it can still look at the application and understand that, oh, okay, this application is currently not working, but at least is still usable up to a point. That's what resilience is all about, or that's what we're trying to discuss here today about resilience. Okay. So, operational flexibility. I'm sure. Has anyone heard of chaos engineering before? Anyone heard of chaos engineering before? Okay. So chaos engineering is the example I gave previously, where, say for instance, the database of your application is dropped. And that can happen to anyone, to any application, for whatever reasons it might be. So with a resilient system, right, the expectation is that you embed engineering into your flow of process, where for whatever reason, whether you just want to test how your application will behave, or you want to see how things will be when a particular thing happens within your application. I'll give another example. For instance, if you have a mobile money application, what happens if your payment partner is not available? What happens? Would your application still be interactable with? Like, would it still work? Or it just throws all sorts of errors? So essentially the idea behind chaos engineering is to stir the pot as much as possible. Stir the pot within your product, within your software, stir that pot throw in confusion by yourself to understand how your application will react, and then begin to see how you can make it better, make more sense to whoever is interacting with your application. Self-healing mechanisms. Design system to detect and respond to failures without human intervention. Believe me, I'm not a novice to this. This has happened to me several times, where even me as the engineer of the software did not know that there was a problem within the software until several customers escalated, right? So what self-healing mechanism does to your system is that it, call it a failover system of some sort, right? Where if something happens within your application where some functions are supposed to happen and then they are supposed to follow each other, if that does not happen, then what next? What next? Does your application just gives up, or does it look for the next best thing to do or to show to the customer? So that's what self-healing mechanisms is about. Observability. Establish deep visibility into systems with real-time monitoring, logging, and tracing. This enables early detection of issue and better root cause analysis. I know with engineers, this is a lot of struggle, because some engineers will tell you, oh, yeah, we are logging, but when you look at the log tells you nothing. Like, you can't make sense of what is happening when you look at the log. So what we are saying here is that even with the tools that you have, whether it's logging, whether it's monitoring, whether it's tracing, there's need for it to have a design, a purpose, so that when whoever needs it, whether it's you or your support team that needs it, goes through it, they can make sense of it, and it gives you a better turnaround time, so to speak. So that's what that observability is about. Resilient culture and continuous improvement. So there are majorly three key things there. So the first one talks about fostering a resilient mindset. So the idea there is for you to, emphasize a culture where learning from failures are encouraged, is visible. In some companies, if there's an issue with whether your product or your software, someone gets a query, right? So it means everybody is on the edge. Nobody wants to see any issue anywhere, not the product manager. Even the QAs do not want to see it. So even before your software before it passes test, the kind of rigorous test they'll do on it, you ask yourself, what is happening here? Like, what are we testing for? So, but that in itself does not mean they don't need to test the softwares rigorously, but it just means that the company needs to be agile. The company needs to be able to learn fast from mistakes, and be able to foster a resilient mindset. If this is encouraged within the company, then what it means is that everybody have a sense of duty. if I go back to the previous slide here, where it talks about the ability to detect and respond to failures, it then begins to make sense, right? Because it's not just the product manager that would do it alone. It's not just the software engineers who would do it alone. It's not just the QAs who would do it alone. It's a team thing, right? So if as a software engineer I'm the only resilient person, then it means I have my work cut out for me, and I would need a community to help me, you know, achieve the things I need to achieve, right? But if you have a community of people where everyone is resilient and everyone understands resilience, it makes it easier. So, feedback loops. I know engineers hate this one. The moment you are going to an engineer and then you are telling him, your software didn't work or your API is not working, the first thing the guy does is looks at you with a bombastic side eye, like, what are you talking about? I tested that. I did not sleep overnight because of that thing, though. So, but what we're saying here is you need to have an open mind to get feedback from your team and people outside your team about what you're doing and how things are going, right? So the last one says cross-team collaboration. Again, I think I had mentioned that while I was speaking about fostering a resilient mindset. So essentially for the cross-team collaboration, what it means is that when you've now gotten everybody's buy-in, it now needs to flow from, from the top to the bottom and then from the bottom to the top, both ways. So that's it, I believe. Thank you very much.